What we'll do now is we will apply the first law to the closed feed water heater in a very similar manner to what we did for the open feed water heater. So with this, we'll assume that the feed water heater is insulated, there are no moving boundaries or no moving parts for work. The other thing is kinetic energy and potential energy of both the exit and the inlet streams will be neglected. And with this, we get a similar form of the first law that we saw for the open feed water heater. Basically, just the mass flow rate of the fluid streams exiting multiplied by the enthalpy is equal to the mass flow rates of the fluids coming in multiplied by their enthalpies. So for the feed water heater, let's go back here and take a look at our schematic. This was what we were looking at, and we had the enthalpy coming in, so we were at state 2, and we also had fluid coming in at state 7, and then it was exiting at state 3 and state 9. So with that, we can write, taking into account the fact that we have mass fractions here, because not all of the mass is going in each of the streams. So that's what we get for the feed water heater. And the other thing that we have a mixing chamber, which is something that's different from what we looked at before. Mixing chamber is basically just a T elbow. It can be as simple as a T elbow, where you have 2 inlets and 1 exit in a piping system. So let's look at applying the first law to the mixing chamber. Now, our fluid streams that we have fluid stream 9 coming in, and 4 coming in, and 5 going out. So 2 in and 1 out. And what is exiting is at the full flow rate. So we have 1 for the pre-multiplier. So that would be the representation of the first law for both the closed feed water heater as well as the mixing chamber. Now, sometimes what we do is we can get away without having to have pump number 2 by using what is called a trap. And when you use the trap, instead of sending the fluid through pump 2, what you do is you send it through a throttling valve whereby the fluid pressure drops down to the condenser pressure. The thing about this, you're losing, well, actually, you're not even gaining energy here. So it's a way of doing this in a slightly more economical manner, in that you don't need this second pump. So we sometimes use a trap. Sometimes also called a throttling valve. But what we're doing is we're throttling the liquid to a lower pressure. And this is a constant enthalpy process. So what we're going to do, we'll take a look at a process schematic and a process diagram for the closed feed water heater using a trap. So what we have here is the process schematic, as well as the process diagram for our closed feed water heater, assuming that we have what is called a trap. So we don't have two pumps, we only have one pump here, and we have this trap device. Now, traps or throttling processes are characterized as being constant enthalpy processes, and consequently, what we can say is that in the trap, H3 equals H8, so it's a constant enthalpy process. The enthalpy will not change. And with that, if we can determine H3, we then know H8, and from that, we can then get the quality at 8, and that is assuming that we know the pressure within the condenser. So that's one thing we can do here. And then the other thing is looking at the first law, or basically the energy exchange in the condenser. We have a slight change where we would have Q out. So we would have that for Q out of the condenser, 1 minus Y times H6 minus H8, which is reflecting the change in this stream with this stream, and then plus H8 minus H1. So that would be the heat transfer out of the condenser. This is the way that we determine conditions through the trap. So that is if you have regenerative Rankine with the closed feed water heater and a trap. So with that, that concludes the efficiency games that you can play with the Rankine. We looked at Rankine with reheat, and we've looked at regenerative Rankine, two types, both open and closed feed water heaters.